Hello teachers, let's talk about section 2-3 today, other set operations and their properties. So the things that you'll be able to do after we cover this section is talk about relations between set operations and logic connectives, and we're going to spend a lot of time talking about Venn diagrams to sort and reason with data. To start off, I want to consider an example. We want to talk about C. Remember, this is set builder notation. We're going to say C is the set of all X such that X is a college graduate, and then a separate set X, S, and S is the set of all X such that X earns at least $40,000. So we have two separate sets. One set is college graduates, the other set is a salary of at least $40,000. Suppose we want to mail a questionnaire to all individuals in a certain city who are college graduates and who earn at least $40,000. Then the individuals to receive the questionnaire include those common to both sets C and S. So the important thing here I want you to see is that when we're dealing with and, okay, highlighted here, it has to meet both of those conditions, right? So and means they're a college graduate and both they earn at least $40,000. So we can set up a Venn diagram. Remember Venn diagrams from the last section to represent that information. And the intersection of sets C and S is the shaded region. So these are the people in green that both are college graduates and earn at least $40,000. Now this is a common idea in set theory. It's called the intersection. So when you want to discuss and between two sets, in other words, sets that meet the elements that meet two different criteria that are in two different sets, that's called the intersections of set A and B. Notice the notation. So you see the notation there? It's like kind of like an upside down U without that little tail on it. You read this as A intersection B is equal to all X, remember the vertical bar, such that X is an element of A and X is an element of B. And again, the super important part of this is the and. So key word is and, which implies both conditions. So I have an example for you. Find A intersection B in each of the following. So we're given the set A, which includes elements 1, 2, 3, 4, and set B, which includes elements 3, 4, 5, and 6. Now, intersection, we're talking about the values that are in both A and B. Notice 1 is in A but not in B, so that's not in the intersection. The number 2 is in A but not in B. 3, if you'll notice, is in set A and also in set B. The number 4 is in set A and also in set B. Now if you take a look at set B, 5 is in set B but not in set A, and neither is 6. So we could say A intersection B is equal to the set 3, 4. Now if I show you the typed version of that, there you go. Intersection B is 3, 4. Let's try another problem. So next we want to take a look at the set A, which is 0, the set 0, 2, 4, 6, and B is the set 1, 3, 5, and 7. And so our goal is to find, again, A intersect B, and that equals, and we're going to list what they have in common. So I'm checking out A, and I have 0 in A, but it's not in B. 2 is in A, but not in B. Hey, 4 is in A and not in B. You see a pattern here. I don't see anything that these guys have in common, because A is the set of even whole numbers, right? Not natural numbers, because it starts with 0. So these are the even whole numbers. B is the odd You could say either whole numbers or natural numbers because 0 doesn't exist in either of those sets. They don't have a thing in common, y'all. So how do I write that? Well, remember the empty set, there's two ways you could write it. You could actually write it with set notation, listing method, and put absolutely nothing in it. Or you could write it using the empty set symbol like that. Both of those are correct. Again, the typed up result looks exactly the same. Now, there's something new that comes for this I want you to realize. That's called disjoint. Whenever you have two sets that have no elements in common, in other words, the intersection is empty, these sets are called disjoint. Next example, let A be the set, it looks like the even numbers, the even natural numbers this time because 0 is not included, 2, 4, 6, 8, and B this looks to be, if I follow the pattern, 1, 2, 3, 4, and then we have some ellipsis dots that which imply this set keeps going, 5, 6, 7, 8, 9, 10, the natural numbers. What do they have in common? But it looks like all of the even numbers. So A is going to, A intersection B, let's use proper notation, is the set of 2, 4, 6, 8, use my ellipsis dots, that keeps going, but that actually matches set A. So the most efficient way to write that is just set A. If I look at the typed up version of that, you'll notice A intersection B is equal to set A. And you always want to write it the most efficient way. It's kind of like simplifying a fraction to lowest terms. And in your homework, you're going to find out they don't want 2, 4, 6, 8. They want it simplified to set A. Now, if C represents the individuals with a college degree and S represents the individuals earning at least $40,000, we can use a Venn diagram to display information. We know this, right? So there's our Venn diagram. Now, if we know that 4,800 individuals have college degrees, 5,400 earn at least $40,000, and 1,200 have a college degree and make at least $40,000, then what could we say from that? Okay, so again, if we know that 4,800 individuals have college degrees, 5,400 earn at least $40,000, and 1,200 have both. That's that green area. That's why I have that highlighted for you. That's the green area. You could put the $1,200 right there in the green area. But now, how do we figure out? So C, remember, that's who have college degrees. There's 4,800 individuals with college degrees. Now, does that go, the question is, does that go right here? Should we put the 4,000, oh, sorry to move that on you. Should we put the 4,800 here? Well, you would say no, right? Because the 4,800 includes the 1,200 that's right there in the middle. So let's don't put the 4,800 there. What do we put in that outside moon area shape? How about we subtract 1,200 from 4,800, which is 3,600, and that's going to sit in that outside area. Okay, so notice the entire circle C equals the total 4,800 for C. Now let's do the same thing to figure out what goes out here in the moon shape on S, the crescent shape. We've already included 1,200 is already inside S, but we know 5,400 total earn more than $40,000 salary. So what if we take the 5,400 and subtract the 1,200 we've already got included? That's 4,200, and those earn at least $40,000. And look where I put that. So outside. So again, you 3,600 plus 1,200 adds to be 4,800, but also 4,200 plus 1,200 adds to be the 5,400. And that's what you're going to do to fill these tables out. You want to start in the center. If you know the intersection value to go in the middle, you fill that in first and subtract to work your way out. often. It depends on the information you're given, so be really careful about the information you're given when you fill these in. Now, let's define something new. Consider the following sets again. You're going to get tired of this example, but all the X's such that X is a college graduate, and then S is the set of folks that earn at least $40,000 a year. Suppose we want to mail a questionnaire to all individuals in a certain city who are college graduates or who earn at least $40,000. So keyword here is or this time. Remember last time we were looking for the people that did both. Okay, so they earned a college degree and they earn $40,000 a year. So now it's one or the other, and or actually means one or the other or both. All right, now what would that look like if you shaded it in a Venn diagram? Well, how about everything, right? So you could be a college graduate, which is the circle on the left, or you could be in the $40,000 or above range, which is the circle on the right, or you could be right there in the middle, which remember was the intersection. And this is called the union of sets, when you just combine two sets together. Definition of that is A union B is equal to all the X such that X is an element of A, or, again, keyword here is or, X is an element of B. So this time we'd like to do a few examples where we find the union of sets. And again, union means the element is in A or it's in B. It's really combining two sets together. Okay, so proper notation, you have A, and then the union symbol looks like a U without the tail, B, is equal to, use curly brackets to denote a set. Now I'm looking at set A first. I've got a 1, a 2, a 3. Now, notice 3 is in both of them, and so is 4. Do you write it twice? Well, you would say no, right? Because you don't list elements more than once in a set. So we have 1, 2, 3, 4, and we've already written 3, 4 that's in B, and we need to include 5, 6. So there is the set A union B typed up. There you go, 1, 2, 3, 4, 5, 6. Let's do another example. Maybe you pause it and do this problem this time on your own. Okay, so we got the set 0, 2, 4, 6, looks like the even whole numbers. The set 1, 3, 5, 7 looks like the odd whole or natural numbers. When I combine those together, A union B, and sets don't have to be written in numerical order, ascending or descending, but it sure makes things a little bit easier to read. So 0 is in set A, 1 is in set B, 2 is in set A, 3 is in set B, 4, you know the drill, okay? And this continues on forever. Well, y'all, that looks a whole lot to me like the whole numbers. I'm just going to put W for whole numbers. What did they put? Okay, A union B is 0, 1, 2, 3, 4. They didn't call it whole numbers, but I don't have any definition that says W is whole numbers. That's the problem. We do know that N, capital N, represents the natural numbers, but we don't have notation for whole numbers, so we just have to list it just like that. Ready for another example? Here we go. So this time A is 2, 4, 6, 8. B is 1, 2, 3, 4. Again, B is the natural numbers, it appears to be. A is the even numbers. You could say that has to be the natural numbers because 0 is not included. When we union these together, remember union means we're just combining the sets together. A union B is equal to, now 1 is not here, but it is over on the right, and then 2 and 3 and 4. That's set B. And then 2, 4, 6 is included in this as well. So this is what we're talking about here, which happens to be the natural numbers N, right? And the typed up version of that, A union B equals B. Now what did I do wrong? Well, let's go back and look. I didn't simplify it like I was supposed to. You notice the N is actually the set B. Now if I was doing this in homework and typed it in, likely I would miss it because they didn't want me to use N. They wanted me to use the most simplified thing I could, which is speaking in terms of the sets that were given. That is just the set B. And I just overlooked that. Okay, so just be careful about that on your own in the homework as well. So this is how they would answer it. They would just enter B, because that is the same as set B. Now let's talk about a new definition. So recap. So far we've talked about intersection, which is and. That means elements that are contained in both sets. Union is an or. So the set could be in one set or the other. You're just combining the sets together. Next I want to talk about set difference. So consider the following sets. C, once again, is college graduates. S earns $40,000 at least. What about the set of individuals earning at least $40,000 but not college graduates? Now we have a name for this. This is called the complement of C relative to S. Also called this set difference. You might find that this is easier to call it the set difference. Because when you look at the notation that's coming, C relative to S, it's kind of backwards. Watch this. Here it is, okay? The complement of A relative to B, written as B minus A. So notice this. It says A relative to B, but when you write it, it's B. Minus. You don't say minus. You actually read it as A relative to B. Or you could say the difference of B and A. And I think it's a little easier to say the difference of B and A. Now, what is that? It's all the elements that are in B that are not in A. So you just take the set B and remove all the elements that are in A. It feels like subtraction. It's not truly subtraction, but it does feel a lot like subtraction. So the notation is not bad notation. But look at the note down here. They point out A that is not read as B minus A. Okay, I'm sorry. Note B minus A is not read as B minus A. Even though I tend to do it, I shouldn't. Minus is an operation on numbers, and set difference is an operation on sets. So set difference is the smarter thing to say here. And again, it's the complement of the second one, A, relative to B. What does that look like? There you go. So you just have the set B, and you get rid of everything that's also in A. Okay? Makes sense? Got more examples for you. If A is the set DEF, B is the set ABCDEF, and C is over there as ABC. We want to find the difference of the sets A and B. Now, a smart thing to do would really be simply to write the set A down, D, E, F, okay, and remove anything that's in B. Now notice that D is in B, so I'm going to get rid of it, okay. Is E in B? You bet. Is F in B? Sure enough. What does that leave us? Nada, right? The empty set, also known as the empty set. Again, you don't have to write both. Okay? All right. How about B minus A? B minus A. So how do you do this? Again, the easiest way to handle it is just write down the set B if possible. And I'm just recopying the set B. And I'm going to remove any element that's in A. Okay, so A, the element A, is not in A. The element B is not in A. The element C is not in A. Finally, D is included in A, so it's got to go. E is included in A, and F is included in A. So that leaves the set A, B, C. Now, I'm going to be a little bit better and pay attention. You know, that happens to be the set C down there. So this is really the best answer. This is the most used answer as far as the empty set. Now, why don't you pause and do this again? We'll see if we match. Okay, so I'm going to write down set B, A, B, C, D, E, F, and I'm supposed to take the difference of sets and remove set C. So anything that's in set B that's written down that's also in set C, I'm going to get rid of. So I'm going to remove the A because A is in set C, B is in set C, and C is in set C. And that leaves the set D, E, F. that might be familiar to you. Set DEF is set A. So the most simple way I could answer that is just to put set A. Finally, the difference of sets C and B. Another way to write this is the complement of B relative to C. Again, that's the more difficult way for me to remember it, but that's what it is. So I'm supposed to write set C down first. That's A, B, C. And remove any elements that are also in set B. So an A is in set B is in set B, and so is C. So that leaves me with nothing, which is the empty set. The set operations have some properties that you should be aware of. One of them is the commutative property. Now, the word commutative, I really like to think about commute, the base word commute, and I'm trying so hard to highlight that. There it goes. What does commute make you think of? Moving around. Commute is your travel back and forth to, say, work. Moving things around. So commutative in math also means moving things around. Notice A intersection B is identical to B intersection A. The order that you do these in, same as A union B and B union A, does not matter. The reason is the order of elements in a set does not matter. So A intersection B is identical to B intersection A. Same thing with A union B and B union A. But as you can imagine, what do you think about the difference? What about A, and I'm not going to say minus, I'm going to say the difference between sets A and B, or you could say the complement of B relative to A. Is that the same as B, the difference of B and A? I'm stopping myself from saying B minus A because that's just not right. But it is a similar idea. Is that the same? Well, we could go back and look at examples. Did we do that on our last example? Check it out. Is A minus B, which is the empty set, equal to B minus A, which is the set C? Aha! They are not equal. So the difference of sets is not commutative. So that's something to think about. When you think about properties, it's a really good idea to think about what else could this property possibly apply to. Again, intersection, union, yes, but the difference of sets, no. You likely remember something called the associative property in mathematics as well. Root word of associative is associate. I always think about associate, who you hang around with, right? Who you're grouped together with. Well, that's what it means in math as well. In this case, if you look at A intersection B intersection C, notice B and C are grouped together because of the set of parentheses. Well, it turns out you could group A and B together as well, and you get the same result. So that works for intersection and union. Notice A union B union C. You could here B and C are grouped together, and then you calculate A union B union, the group. Or you can group A union B and do that calculation first, and then union that with C. Again, since the order of the elements doesn't matter, you have an associative property. There's even a distributive property, which is pretty interesting. What does this really mean? Notice here, grouped together is B union C. Okay, on the left, B union C are grouped together. So you would do that calculation first, and then you would take the set A and find out what's common between A and B union C. But if you like, you can, watch this, group these two together, and then separately, with the intersection included, group these two together. And notice that symbol that's in the middle turns up in the middle there. So that's like a distributive property for intersection over union. It says use set notation to describe the shaded portions of the Venn diagram. So we want to try to describe what we have going on here. Now, what do you think about this? We're trying to use set notation to describe this. Notice what's shaded. We've got, this is the green area, the outside of A and the outside of B. right? It almost looks like A union B, but the middle part is not shaded. So how could we do that? What if we did this? What if we said A union B, again, and get rid of the middle part? So subtract out, which remember is not truly subtraction, is the difference in sets, A union B, and subtract out A intersect B. Does that work? Now, can you think of another way to describe it? That's certainly not a unique answer. There are other ways to describe this set using set notation. You could stick with the A union B. You know, always, if you use the difference of sets, there's another way to describe it, but sometimes it's more complicated. My pen quit working. Here we go. How about A union B again? Again, A union B covers everything in A and everything in B, so if I were to shade just A union B, that center white part would also be shaded. Now, what if we try to intersect that with whatever is not, so that A union B in common with, let's get rid of that. So that would be a complement. How about the complement? Remember, the complement means everything not in a set of A intersect B. Now that one might be a little bit harder to see, but again, A union B gets rid of includes the center part. Okay, so that would be included in A union B. But we're going to say what that has in common with A intersection B complement. Now, A intersection B is that center part that I just shaded, and the complement would be everything outside here. Now, it's what the green and yellow have in common, which basically is just this green part right there. Okay? That one, again, might be harder to see. Let's see what the book decided to put there. Okay, so look at the first answer. This A union B and the difference of A intersection B. That's the first way we attempted it. And that was probably more clear because A union B does include the center, and A intersection B is the center that we just minused or differenced out. Okay. Next one, hey, there's that second one we did. A union B, remember that's the whole thing, including the center white part, intersected with what's common with everything that's not the white part, which really just gives you the green part. And they've got a third one. It says the difference of A and B. Now let's just try to draw this on our own. Not nearly as pretty as theirs, but there we go, A and B. Okay, so the difference of A and B, let's do that in yellow. So all of A, get rid of what's in B. So that's this part. Okay, union means you combine it together with the difference, we'll do a different color, of the difference of B and A. That means everything that's in B but not in A. So wouldn't that be this part over here? And then when you union them, you make them all the same color, and that definitely gives you what we have right here. I like it. That works just fine, right? This is not an easy thing to do, so just be patient with yourself. You want to try another one? Why don't you pause it and see what you can do with this one? Of course, this has got 3 sets. But see if you can come up with at least one way of writing this set using set notation. Now, what'd you come up with? Okay, I'm looking at this. I'm going to highlight it right here in yellowish now. How could we write that part alone? I would say that is A intersect B. Right? Intersection means and. It's what they have in common. And then the other part, I'm going to highlight it in kind of some aqua color. There we go. What could we call that? Well, I would call that B intersect C. Now, how do we combine those together to get that picture? That's what a union is for. So you could put these in parentheses. and put a union symbol between it, and boom, there you go. Now, we had the answer A intersect B union B intersect C. Where did they come up with this? Well, remember, this is that distributive property that we spoke about, right? They have this B in common. That can come out, and the common intersection, and then you combine the A union C. That is just the distributive property, so it's another way of writing that same set operation. Here's another one. Please pause it and see what you can come up with on this one. Now what I see is we have A shaded, but we've removed everything that's in B or C. And notice I said or. Hey, that's important. So what if we took A, the set A, and we're doing a difference of sets, A, and remove B union C. And B union C would be all of this part. So we took A, which is the whole set of A, and removed anything that's in B union C. So that would definitely work. I'm going to get rid of all my shading here. Can you think of another way to do it? If so, let's just look at their list and see if your answer made the list of answers. So notice the one that I wrote down is actually the second option listed, the set A minus the union of B and C. Let's take a look at the first one. And then again, I shouldn't say that. It's such a horrible habit, but I'm saying A minus B union C. It's really the difference of A and the set B union C. The first option is the set A and the difference in B. So I take all the elements that are in A and remove what's in B, which would be this part. And then I remove what's in C, which would pick up this part. I could see that that definitely works just fine. What about the next one? We're taking A. Here's my scratch work. We're taking A once again. Okay, the whole set A, including the little leaves right here, and subtracting out A intersect B, which A intersect B is this part. Oh, no, it's not. That's B intersect C. A intersect B, I need to be careful, is this part. What else would we need to subtract out? Let's take a look. A intersect C, which if I shade that in a different color, would be this part. We happen to subtract out that little triangle shaped thing in the middle twice. Is that all right? Sure. As long as we're left with what we need. So I like both of these. I feel mostly comfortable with the one that I had highlighted, of course, but I like them both. Now, I've noticed that I've gone over my time again. I try to keep it to 30 minutes. You probably already know this. So when we come back for part 2, I'm going to pick up another one of these examples. As a matter of fact, I'm going to go ahead and show it to you so you can be thinking about that. So part 2, I'm going to start with this example, see if you can come up with sets for this. Okay? Otherwise, you have a good day.